3.1, Part D now. I'm sorry, Part C. We did A and B earlier, Part C. So this is in charging methods. So how do we take materials, atoms, whatever they are, and have them charge up? So if every electron had their way, they would be bounded to protons, and we would never know that charge even existed. So when paired up, the positive charge of the proton and the negative charge of the electron cancel each other out, and it all appears neutral. But there are three basic methods by which charges can be persuaded to rearrange themselves, so they may be detected. And the first one is charging by chemistry. And it has to do what we talked with in the last part where we discussed electronegativity, on how well materials hold on to their valence electrons. So we were sort of talking about atoms before, and how different atoms have different electronegativities. We go to materials, they also have different electronegativities, and we break them up into insulators and conductors, and you can do the same with atoms. But this relative electronegativity, so separation on relative electronegativity, one's more electronegative than the other. So a relative electronegativity scale is called the triboelectric scale. Okay? And so the triboelectric scale is used to put different materials based on which is more electronegative than the other. Okay? So we could have a simple well depth, our well depth model, like so, and that would be more electronegative than this one, with the shallower well depths. This depth here being more than this depth there. So when you charge by chemistry, that's what we're really talking about. It's a different chemical property, the different electronegativity that leaves, when you bring these into contact with each other, so like this one over to this one, some of the electrons will transfer among them when they're in contact. And a lot of times this used to be called charging by friction, because you have to put them in contact and move them around to get them. But it's not friction that's charging the thing, but they call it that. But it's when you put them in contact and move them around on each other, then some electrons will transfer over to the other more electronegative object. So the one that's more electronegative, that has a higher ability to hold on to electrons, will pick up relatively more electrons than the other one. Not all the electrons, but relatively more will transfer over. And for this to work, you have to have two insulators. And that's because the electrons need relatively deep wells to get trapped in. Okay, so how does this look? Let's look at this schematic that we're going to be using for charging by chemistry. Well, we'll use it for the other charging methods as well. But with charging by chemistry, by convention, we have to come up with what neutral means, because if we took a square like this, we know that it's filled with a bunch of positives, billions upon trillions of them, and a bunch of negatives. And I'd be here for the rest of my life and many lives after mine to fill that in. So by convention, we look at this empty box is the neutral box, okay? And then if it has excess charge, well, we add the excess charge onto it. So here's a sketch for charging by chemistry. In A, we have two blocks, like so, separated and both neutral, okay? In B, we're going to bring those blocks together, and we're going to move them up and down, back and forth, like so. And in the process of doing that, some electrons will end up trapped in more so in the one with the higher electronegativity. And therefore, we could end up with a net charge of, if the electron's transferred over to the block on the right, then we will end up with the block on the left being overall positive charged, and the block on the right, because it gained extra electrons, having an overall. Here, we could still see in this process that the sum of Qi, neutral, is sum of Qf, also neutral, 4 plus is 4 minus. So that would show charging by chemistry. The next method we'll look at is charging by conduction. So charging by chemistry, we see that we need two insulators. We need the deep wells. Charging by conduction, you need two conductors. Okay. The second method of charging an object is by touching it with another previously charged object. And we need two conductors for this to work. In the conduction phase, when the electrons start to move from one to the other, it's no longer static, so we're into the dynamic realm, which we'll talk more about in the next unit. Okay? When the charge conducts, it redistributes itself across the objects. Because the valence electrons for conductors are able to move around freely. Well, why does it redistribute itself? Because if we have, say, an object, like so, a bar of something, and it's got 4 electrons running around it, and we touch that to another object that's also a conductor that's neutral, like so, then I'm just pausing because of the board is shaking as a train goes by, but it was shaking more than it normally does. I don't know if the train's heavier or what. You could hear the whole building shake. So anyways, in this case, these electrons will redistribute themselves across the surface, actually. In fact, do it so that they'll arrange to be farther away from each other as possible, maybe something like that. I don't know if that's the right arrangement, but in so doing, they want to get as far away from each other because they want to minimize the repulsion that they feel because they're two negative charges, and two negatively charged objects repulse, two positively charged objects repulse, a negative and a positive attract. We'll look at that for you. By the time you watch this, you should have looked at that already, some demos. And so that it has to minimize that repulsion, okay? So the electrons split up to move around the object. And this explains like charge leakage on humid days. Objects that are charged will lose their electrons, and what they lose it is to water in the atmosphere. So here is a sketch of charging by conduction. So again, we have the two blocks. But remember, we said the first start, we had to start off with one already charged. And then we put them together, touching each other. And we could see that the electrons will transfer into the neutral object. So the electrons transfer. And then in the third sketch, we'll just show how those would transfer. Well, if they redistribute themselves equally, and it's an equal area here, then we could see that we'll have 3 negatives there and 3 negatives there. So it's based really on the surface area of the objects on there. So let's look at another example, because we don't have to start with negative, okay? So in this example, we'll start with a 2 positive here. And that means that it's down 2 electrons, right? 2 electrons have left of the billions upon trillions that are in it. And so, which way would the electrons go this time? Is that what you said? Good. So, in that case, just one electron will go over, or 1 unit of charge, if you're looking in that case, and the plus. Each will be 1 plus, okay? Check out this example where we take a small item with some charge and a big item based on the area of these is how the charge will redistribute itself, okay? So we know when they touch that the electrons are going to transfer over, but how many transfer over? Well, it's actually based on its surface area. So by the size of these, just guessing in this sense, I don't have the actual amounts. Maybe we have 1 there, and then over here we would have 7. And that's the idea of grounding. In grounding an object, we can connect it to some large piece of metal and distribute the charge through. So a house itself will build up a lot of charge on it. And so that charge, if it's built up through electric wires and things like that, we want that charge to go somewhere where it can distribute itself. Well, one place it can go is in the earth, okay? And so you could have a connection, and what they connect to now is like these large, the earth is a large conductor. But one way that's easy to connect to the earth is through the large metal pipes that run through the city of Buffalo, things like that. So we have grounds in our house, the grounded circuits, the grounded outlets, and that takes any excess charge that might build up, and it distributes it into the large sewer system pipes by just connecting it to a pipe in your house, and then that way then no excess charge will build up in it. And so that's called grounding. The third type is charging by induction, and I may end up having to pause this, but let's see. Charging by induction is the third type. And charging by induction has to do with things like take a balloon, right? Rub it on your head, it sticks to the wall. Now the wall itself is neutral. We know that. So how does that happen? Well, something must make it charge for it to stick to the charged balloon. The balloon gets charged by chemistry. You're rubbing it on your head, you're putting it in contact. You have your hair, and you have the rubber from the balloon, and some electrons are transferred there, and the balloon becomes charged. A neutral object is not empty of charge, though. The wall is not empty of charge. It's just in balance. The total number of positive equals the total of negatives. But when you bring the charged balloon close to the wall, some of those negatives that are in it are going to move and shift away from the wall, making the portion, that pocket on the wall, act as being charged when that charged balloon comes towards it. So we call that charging by induction. Okay. Now there's two, insulators and conductors will work for this, and we'll have to look at two models. So let's start with insulators. And we'll look at using our well model here. So let me take an insulator like so, and let's take a charged object. When we don't even have to actually touch it, but just bring it close, the charged object close, these are able to shift around. Now the negative's not going to shift towards the negative, it's going to shift away from it. So it shifts in its wells, you see? So they'll shift away from the charged object, leaving this redistribution of charge in the insulator here, causing this pocket of it to behave where this is more positive and that's more negative. So that charges it. That's called charging by induction. Charging by induction in conductors looks similar to charging by induction with a conductor. In this case, you bring it close. Some of the negatives might shift right out. They all are shifting away from the negatively charged to the one side to get as far away from it as possible. Okay, I've run out of time, so let's look at the rest of this, which is just a short little box sketches and stuff, and static electricity and electroscopes we'll look at in class.